Hello ladies and gentlemen, and welcome back to Prospect Charter School's Algebra 1 course. Today we are going to be going over section 5.10, Transforming Linear Functions. This is the introduction to something that stays with mathematics all the way through calculus, and that is families of functions, a parent function, and the transformations that take place. In fact, in Algebra 2, I would say this was the most important lesson of all. Alright, so let's start with those definitions. The first definition is a family of functions. Family of functions. And what a family of functions is, according to the textbook definition, is a set of functions, so a set of functions whose graphs all share basic characteristics. I can't fill that in there. Characteristics. So, you know how a family is, right? Everybody, you have the mom who's really awesome, and then you have the dad who's usually kind of awesome, and then you have the kids, which are kind of half mom, half dad, and that they love doing kind of the same things. And there's a little baby kiddo. And you know that the baby functions take different characteristics of both the mom and the dad, so that they have like similar hair color, similar eye color, similar facial features, etc., etc. Well, when it comes to functions in a family of functions, that's pretty much the same thing. We know about graphs, and we know that all lines look alike. They might have different slopes, they might have different starting places, but all lines are just that. They're a straight line that go in a specific direction. And we can have a whole family of these. We can have all kinds of them going in different directions, in different ways, but we know that they all fit the same kind of category. They're all the same family. But a different family from, say, a line would be something called a parabola. And parabolas look a lot different than lines. Well, for one, they're curved. For two, they tend to go in the same direction. They do all kinds of different things. So that would be a different family. And then you have things called cubics, and cubics look totally different from our parabolas and from our lines. But they all share certain characteristics. So a family of functions is a group of things that look a lot alike. So example would be lines. Which brings us to our next portion. Just as a family has a person who is the father or mother of the family, and from whom everybody is beholden or derives all of their characteristics from, so too do functions. Functions have a parent function. And the parent function is the most basic function in the family. The most basic function, if I could draw you today, function in the family. So where before, or in a regular family, your parents would have usually a lot better education, a lot more life experience, a lot more stuff that they've gone through and can understand and anticipate. Well, here it's kind of the reverse. The parent is the one that's the most basic, the least complicated, the one that we transform to create the rest of the family. So for linear functions, that parent graph is y is equal to x. Y equals x is the McDaddy of all lines. It is the parent function of all lines, and all lines derive their transformations from this particular line. Y is equal to x. And from there you can have transformations. So a transformation is a change in position or size of a figure. A change of position. How do you spell position? I-T-I-O-N. Position or size, which we often call scaling, of a figure. So a change in the position or size scaling of a figure would be a transformation. One of the easy transformations is y is equal to x plus 2. The transformation here tells me that I'm going to shift up 2. Now if we look at our parent graph, it goes to the point 0, 0. But with this plus 2, I know that I'm shifting up 2, so I go up 2 spaces, and I recreate my parent graph at x plus 2. So this kind of a transformation is called a shift, or a translation. And then there's also another translation that we could do, which would be something like y is equal to x minus 3. Well, again, we go from our parent graph, we go down 3, and we recreate our parent graph. We follow all the same rules of the parent graph, at least until we move out on our own, in which case we're no longer, well, you're still part of the family. It would be a little bit different, I guess, for math compared to people, because when you leave your normal general things in math land, you are no longer part of that family. But in normal land, at least hopefully, if you change and become something different, your family will still accept you for who you are. So, with these we have transformations. These are shifts, meaning that we picked up our parent graph and moved it in 2 different directions. But there are other types of transformations other than these. These are called translations. So I'll write that down. Translations, and we'll put it in easy terms. Move the graph. In other words, we shift up or down, left or right. So a translation shifts the graph or moves the graph. Now there's another type of transformation that is called well, they call it in your book a rotation, which is a really bad one. Same thing with reflection. But I guess we can go over it for now. Another transformation would be a rotation. And a rotation picks it up and changes its orientation. So a rotation is a transformation about a point. A transformation about a point. A good example of a rotation is usually in your car. You have something that looks kind of like this. And I think you know what this is called. Yep, it's supposed to be a steering wheel. Now if I take this steering wheel and I move it over to the right, we'll note that most of it remains relatively the same, but its orientation has changed. This is what's called a rotation. Now what about on graphs? How does this apply to lines and line functions? Well, you do the same thing. You have your parent graph through the center at 0, 0, and it looks something like this. Actually, it doesn't look something like this, it looks exactly like this. As long as Mr. O'Neill draws a straight line, which we know is impossible. And then it takes it and it rotates it. So it'd be like taking this end and bringing it down, taking this end and bringing it up, and getting a graph that looks something like this. This would be, sorry about that, this would be the graph that's been rotated. Now our parent graph is y is equal to x. But our new graph, our rotated graph, would be a rise of 1 and run 3, so that would be y is equal to rise of 1, run of 3x, or 1/3 x, as this case is. So a rotation rotates it about an anchor point, and usually that anchor point is whatever our shifts have done to it. So if we shifted up, then the anchor point would be shifted up. If it shifted down, then it would have been shifted down. So that's one kind of transformation, is the rotation. The other kind of transformation is something called a reflection. And I think you know what reflections are. Yep, you see them every morning in the mirror. So a reflection is a transformation about a line. A transformation about a line. So let's say that we have our parent graph, which is of course y is equal to x. And if I was to take this parent graph of y is equal to x, and I was to flip it over the horizontal axis, the x-axis, then this point would move down to here, this point would move down to here, this point would move up, this point would move up, and this point would move up, and we would suddenly have a very different line. I think we know what this line is called, right? Yeah, this is the line y is equal to negative x. So it looks like that rotations and reflections are controlled by the multiplier. So this multiplier controls reflections and rotations. And later on, we will see that it controls a lot more than just that. But that's for another day. For now, we just know that the multiplier of our x value obviously controls reflections and rotations. So let's go on to the last part of this, which is what happens when we put them all together. So we know what our parent graph is. Our parent graph, the Mac Daddy of all lines, is y is equal to x. Now we already know a particular equation related to this. Y is equal to mx plus b. And what we're going to do is we're going to look at how this transforms our parent graph. The b portion controls the vertical shift. It makes it go up, makes it go down, and because lines are weird, it also kind of makes it go left and right, but we're not going to get into that. B for now controls the vertical shift. The M portion controls orientation and scaling, which is also rotation and reflection, at least for lines. So our slope controls our orientation and scaling, our B controls our shifts up and down. And all lines come from the parent graph, y is equal to x. And that, ladies and gentlemen, is it for today. And for some reason my computer does really weird things when I go to the edges. I want to find a way to turn that off because it's quite annoying, but that's something for another day. For now, however, it's before you go work. So before you go. Before you go, I think you guys need to have a little bit of practice on this. And this is going to be section 5.10, hashtags, math is awesome, 1 through 19 odd. And because I care, I think we're going to look at a couple of others. We're going to look at 35 and 37. So there you go. Pretty easy homework assignment. Well, sorry, before you go assignment. Should be able to finish it before you leave for today. Alright, good luck and have fun.